Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and here with me as always,
Robert Moore.
so Robert. This is the 21st episode, season number 2.
Yeah.
They're adding up.
They're adding up. That means we're probably out there, getting close to 100 episodes total?
It's getting there.
Yeah.
You know what today is?
October 1st?
October 1st already. So we're,
Yeah.
three quarters of the way through this year.
Indeed. And still waiting on fall to show up.
Yeah, it's been pretty warm. I mean, today is a little bit cooler,
But it's going to warm back up.
yeah, it's been really nice around here, so we can't complain, that's for sure.
I like it a little cooler, but
You'll get it. Hang on, you'll get it. You'll get it.
I might be eating those words in a few months.
Yeah, 3 months from now you'll be crying. Oh, it's so cold outside.
Yeah.
So we'll see what happens there. But there's lots of stuff going on in astronomy.
Yeah.
And to update people, one of the major things that's going on is the talk of this comet.
Comet. Yeah. It's the first naked eye bright one we've had in a while, isn't it?
It is. It's been a
Yeah.
while.
In fact, Northern Hemisphere, we should be seeing it early in the morning, right around sunrise.
Yeah, just before sunrise, you can see it off to the just slightly southeast. But it's a very difficult target, and from our line of sight, it's getting closer to the sun.
Is it getting closer?
Yeah, and so it's going to eventually go on the other side and be an evening object, and that's
Right.
coming up later on this month.
Okay.
So in the middle of the month, so we're going to be a little bit more specific, Robert here is actually going to give a talk
Oh, that's right. I am. Oh, my.
on October 14th.
Yep.
And by the time we get to that talk, the comet will be visible after the sun sets.
Oh, so we're going to make that a target?
Well, it's early, so we're going to have to switch around things. And we usually have, for those who don't know, after our talk's over at roughly 9 o'clock, we usually have people go outside if the weather cooperates and look at through telescopes at various things like the moon and so on. And this time we might have to change that because by 9 o'clock, the comet is going to be too low to the horizon on October 14th.
So we might do it before my talk.
That's what I'm thinking, that maybe
Okay.
we can set up some telescopes somewhere around maybe 7 o'clock
Yeah.
local time and see if we can get the comet, because that would be great.
That would be great.
Students get a chance
Yeah.
to see a comet.
I mean, I'm going to say I'll take a cut into my time for the talk for people to see a comet.
So we'll just see how it goes. Of course, it all depends on the weather, unfortunately, right?
Right.
And we never know whether it will cooperate.
Right.
And plus it's low to the horizon. It means you have any clouds at all in the west.
Right.
That could be enough to cover up the comet and you wouldn't be able to see
Or
it.
building or anything else.
Yeah, let's imagine it's just a matter of walking around. Thankfully, we live in an area that's relatively pretty flat.
Yeah.
So you might have to just, step around some buildings to see it in between buildings.
And not that many trees here in the
Yeah,
eastern part of North Dakota.
that's right. So if you told your kids to go build a treehouse,
I think they're going to be out of luck.
exactly. So we have that to look forward to. So, and comets are notorious for not being able to predict their brightness properly.
Right.
There's been a lot of things that happened in the past where the news media would say, "Oh, the comet's going to be super bright." Even NASA said, "Oh, the comet will be super bright," and then it doesn't occur.
Right.
I guess that happened way back in the 70s. Comet Kohoutek, NASA had promised that would be a really bright comet, and didn't turn out to be the
didn't turn
case.
out. Yeah.
And like I said, they're really unpredictable in terms of how bright they get. In fact, the astronauts on Skylab at the time actually photographed the comet. So if you're in space, you get a good view of it. But of course, down here on Earth, it was like, ho hum, why did you get me awake for this thing?
Well, why did I wake up at 5 a.m. for this? Yeah.
So we kind of got to watch our predictions. So we don't know how bright the comet will be. If some media sources are, many times the brightness of the full moon, it's going to be so bright you're going to see it in the daytime sky. Well, it has been bright enough that you can see in the twilight, like the beginning of the day. But whether you could see it, at noon, for example, right? And it'll be above the horizon at noon because it's close to the sun.
Right.
That's a different story. And so it's not quite that bright now. It will get that bright. Who knows? Probably not, but we'll see.
Yeah.
And then,
I still love the fact that the best comet hunter right now is a telescope aimed at the sun, because it sees all the ones that dive into the sun.
yes, SOHO spacecraft.
SOHO, yeah, the best comet hunter we've had.
Yeah, so there's on the website, if you look up SOHO, you can actually look at the feed coming from SOHO, and people actually watch the feed and it takes images, and you can just look at the time stamp of those
Timestamp.
images and go forward, so you can have like a movie essentially, and you can watch comets impacting directly into the sun.
Right.
And a lot of them comets we didn't know they even were out there, right? It's hard to see because they're near the sun, and if you come from the right direction in the daytime sky, you're not going to see it.
Right.
And so we've been surprised a few times where these comets have hit directly to sun, and
Holy
we
cow.
always worry about the one that may come our way.
Right. Comes out of the sun, comes from the direction behind the sun.
Yeah, so it orbits, it gets slinged around the sun heading in our direction, so
Right.
you have several weeks or a few months to do something about it.
Yeah, good luck.
Yeah, well, we were talking off camera just a few minutes ago. That's another reason why you want to keep investing in science and space
program.
technology,
Yeah.
because you never know where all of a sudden you need that defense
Right.
to go up and
And despite
deal
what the
with
movies show, nuking it isn't an answer.
yeah.
So,
That's the problem. There's no easy solution. In fact,
not.
the more time that you have, the better you can
are.
deal with it.
mm-hmm.
And there's been a lot of ideas. You could put like a massive object near an asteroid or a comet, and its gravitational interaction with this artificial object that you put up can actually cause it to deviate from its trajectory.
Yep.
So if you wait many, many, many months later, by the time that object gets near us, it's deflected by enough of an angle that it will miss the Earth.
Right.
Might come close, but it
And-
will miss. And that's the important
Maybe
part.
we ought to do a show on that, on the proposed mitigation
Yeah,
efforts.
Be a good idea, because if you want to spend some money, at least enough to keep our technology going, that we can get out into space, there's a good reason right there. And like they say, if the dinosaurs had a space program, they'd still
They'd
be
still
around
be
today.
here. Yep.
But their little hands maybe couldn't touch the buttons, right?
Well, would they have rained little? That's a good point.
So, and there's actually been discovered another comet. So the
Another one?
Atlas survey, which is surveying, looking for comets and so on, it's actually picked up one just a couple days ago, and that should supposed to make an appearance later on near the end of October. And
Okay.
it could be a bright, quote unquote, could
be a bright one.
a bright one as well. So we might get lucky in a few strings of comets
Right.
coming our way. It's been a while, as you mentioned. In fact, the last really good one, there'll be two of them. A comet, Hale-Bopp was one.
Hale-Bopp. That was in the 90s, wasn't it?
Yes, that was in
Yeah.
the 90s. And Hyakutake was in 1996,
Okay, I remember that one
I
now.
think. It's around that time.
Around that time.
Or it could have been 94, 95, I can't remember. But that was an also very bright comet.
I remember Hale-Bopp because I was taking a numerical analysis class, and the professor canceled class so we could walk across campus to the observatory to see Hale-Bopp.
Oh, nice. Yeah, Hyakutake, that was before Hale-Bopp. And I remember viewing that from a very dark place in Nova Scotia. 'Cause I was there, living there at the time, and it was right across the sky.
Oh, you're
The
right.
comet was directly overhead from my location,
wow.
and the tail went all the way down to the horizon. So it was at least a 90-degree tail on this comet.
Yep.
And in fact, I've seen Comet Halley in 1986 when it made its last close approach, and that was really low in the sky for northern hemisphere.
Yep.
But this comet, Hyakutake, that's the most spectacular comet I've ever witnessed, including the tail part of
Didn't
it.
get a chance to look at that one.
It was amazing. Of course, I was in a dark location, away from city lights, so I had a fantastic view of it.
I got to admit, all the astrophotography I did before coming to North Dakota, I only ever got one comet that I captured the comet and the tail, and you can tell it was right before dawn because the whole one side of the frame is just lit up in white, and then it grades out and you can see the comet.
Oh, nice.
So I got it right as dawn was happening.
I was reading an article a couple months back where they were about comets, and they mentioned the great comet of the 1800s. I think it was like 1886 or something like that. You can look it up. It was extremely bright, so bright, easy to see in the daytime sky.
Right.
Easy.
That's rare, though.
That is
so
extremely rare. In fact, in the 1800s, there were a lot of bright comets that
Okay.
were viewable from the Earth. And in this century, not so much, right? We're just
Right.
starting, of course, but in the 1900s, there were relatively few compared to the 1800s.
Right.
So it's just fluctuations, right,
It's-
in the number of comets.
Just
remember
being
people
around at the right time and seeing it.
And you remember people tried to make a significance to those fluctuations? Do you
yeah.
recall that story? Do you want to say something about that?
If it's the one I'm thinking about, it's that people believe that it has correlated to the cycle of the Earth going above and below the galactic plane.
Well, it's related to extinctions events.
Extinction events, yeah.
And so the idea is that there's this other star in orbit around our sun. So it's a binary star, so Nemesis.
Yeah, Nemesis.
And it's on a really highly elliptical orbit. So the star, the companion, if you like, the sibling to our sun, is so far away we haven't seen it yet, haven't discovered it yet. And as it comes inbound, right, it periodically will disturb the Oort cloud of comets.
Right.
And so it would send all of these comets at a relatively short time scale coming inwards.
Right.
And so you have a lot of these comets passing by the Earth relatively close together in time.
And my statement of that is kind of like, Planet 9, as out there. We've done infrared sky surveys. So while
there is a Planet 9, Robert, it's called Pluto.
Okay, yeah. All right.
You mean other than Pluto?
Okay, yeah. Anyway, we've done full sky surveys in the infrared.
Yes.
Even if these planets are the star, were dark, invisible, it should still be lighting up the sky in infrared. See the James Webb images of Neptune and such as that. So where is it? Where is these bright infrared objects if there is a companion star or a companion dark star or a companion another high mass planet out there? When you can explain that one, I'll start believing that there's another big planet out there or something like that.
Yeah, a star is harder to hide.
A star is much harder to hide.
And you could pick out the stars that are the less luminous, the less intrinsically bright. These would be like low mass stars if you think about main sequence stars.
Right.
That are being similar stage to what our sun is in. And if you're forming stars, you could think that, probably a good assumption that the stars would form at approximately the same time.
Right.
So these very low mass stars, to have objects that are intrinsically very faint, and they can last upwards to a trillion years on the main sequence, happily converting hydrogen to helium in their cores.
Right.
And so you could hide this, you could try to hide it, and by having a low luminosity is very difficult, intrinsically hard to see. So if it's a certain distance away from us, it would be very faint. And you got to pick this out of all the other stars you see in the sky. But we've looked for these things.
We've looked for
with all kinds of surveys that's been done in the last several decades.
Right.
No sign of a star like that. And the planet is the same kind of thing. There's been a lot of talk recently in the last 10 years about, another planet beyond Pluto, right?
Beyond Pluto. Another major
planet, not like Pluto. And one of the reason for it is if you look at the periodicity of comets, you look at their orbits, there seem to be collection of these comets, family of these comets, that may point to a common gravitational perturber.
Right.
That is a body that, any object with a mass that passes through the Oort cloud, which is this huge cloud containing comets, leftover debris from the formation of our solar system. And we're talking going way out there. In fact, it would go halfway between here and the nearest star to the sun, that sort of scale. And you think of a sphere with that type of radius, let's say 2 light years in radius, that's a huge volume of space, a huge volume of space. So it's not like Star Wars where you're shooting down, was it asteroids in the original movie or something they showed that? It's not dense like that.
The chances of successfully navigating an asteroid belt are
pi squared over 3.
Yeah.
So the thing is, these objects are going to be hard to find, and the periodicity in the comets suggests maybe there's something out there we haven't found yet. That's the argument.
Right. And what I'm saying is anything big enough to do what they're saying should be glowing in infrared. Maybe it is dim in optical, but it should be Uranus. It should be Neptune. It should be bright in infrared.
Right. So if you don't find them, you try to hide them.
Right.
And one way you could hide them is instead of orbiting roughly in the plane of the solar system where the rest of the planets orbit, you could put it on essentially a polar orbit. So let's say 90 degrees with respect to the plane of the solar system. So you're looking above the plane and below the plane to try to see where it would be in its orbit today, type of thing.
Right.
But that is difficult, and that's sort of areas where people looked less often. So it'd be easier to hide a planet in those areas. But these infrared surveys are all sky surveys. So they're looking in all different directions, including above and below the plane of the solar system. So far, we haven't detected anything. Does that mean that it's not there? No, you can't say that. It could
You can never prove a negative.
Right. So people are still looking, right? They're still trying to understand these sort of periodicities, like I said, in the orbital parameters of these comets that we know that do exist.
Right.
And that issue hasn't been solved to everybody's satisfaction yet.
And that's one of the solutions is like you were saying about the Oort cloud comets. They're going to be hard to spot. So maybe the matter is we've just spotted these clumps that are in the right place at the right time to make it seem like they are. That starts stretching probabilities, though, and I get why they're saying that, but...
Well, if these objects are really far away from the solar system, a few of them come inbound once in a while from the Oort cloud. That's how we know that exists out there. And the other thing is, too, there could be something that disturbed those orbits very early on in the formation of the solar system. And now is no longer there, but that fossil would be preserved.
And from what we're seeing from forming young star systems with young planetary systems forming up, stuff could easily be being ejected during that time period. And what I mean by that is that it, through gravitational interactions, it's thrown out of the solar system. But on its way out, it could have perturbed these orbits.
Yeah, because you could take an object that's completely symmetrical in terms of its rotation about one axis, and you give it a torque. So now it's, let's say you can do it in the right way, so it's now rotating about multiple axes of rotation. How are you going to stop that? You have to apply another force in the right way to stop that motion.
Right.
So that motion is going to be maintained. In fact, there are even asteroids in our solar system that we've observed that are rotating around multiple axes of rotation, right?
Yep.
So different moments of inertia, if you can think of that, right? Different values depending on how you calculate relative to the rotation axis. So they can be very complex type of systems.
What we're talking about is using this remote control as our asteroid. It could be rotating this way, it could be rotating this way, or it could be rotating that way.
All at the same time.
All at the same time.
So
that's a much harder thing for me to do.
So for an aircraft, that would be trying to control yaw, pitch, and roll all at the same time.
All at the same time. And experienced pilots will tell you that gets real tricky.
That separates the good from the bad, I guess.
I guess.
Your piloting skills, right?
Right.
Okay, but we can think of other stuff going on too in the solar and the universe, right? So lately, there's this paper that just came out earlier in September, so late September, regarding a very interesting find, and this involves black holes.
Right. We like talking about them on this podcast.
And there's a reason for that, because they're very mysterious.
They're mysterious and they're interesting. They do interesting things.
And we don't talk about apples too much because we know what apples are. We know what they're made of. We know what they taste like. We know what they feel like. You know, all these. And then you move on to things that are more mysterious.
Right.
Remember the quote from John Wheeler? It was about, if you're in science, what you should look at the weird stuff first.
The weird stuff. Yeah.
And see why they are weird, right? So that always captures our attention, looking at strange things. In this particular case, it's a black hole that has jets. So there are jets of material that emanate on both sides of the black hole that go outwards into space.
But I thought nothing could escape a black hole.
Yeah, so these jets are launched outside of the black hole, per se, where the outside means out further away than the event horizon.
Right.
Where you don't need speeds exceeding the speed of light to get away from the black hole, which as far as we know would be impossible. So jets are launched outside the black hole in what we call an accretion disk. Now, the exact mechanism of how these jets are created and how they maintain themselves is not 100% known. We know it's interaction of magnetic fields along with a very heavy charged particle environment like a plasma environment. So there's lots of complicated hydrodynamics type of stuff that's going on here.
And I don't think there's any assumptions that can be made. Like with a star, you can assume local hydrostatic equilibrium and get to where you can model the surface. I don't think you can make those assumptions with black holes, can you?
You can as a starting point,
Okay.
right? And then you got to
But
get
then
to
you gotta,
yeah.
yeah.
Like the cow is a sphere, and then you well, how do you get milk from it? Okay, so we got to get more complicated now, right?
So, you know, with a star, stars are pretty much spheres. They do certain expected things. It's really, well, not real easy, but it's easy comparatively to get from that local looking at a small piece of the star and assuming it's in equilibrium to getting to the whole star and saying, oh, okay, it's in equilibrium. So,
And then when you look at stars themselves in detail, you find they're not all spheres. They're more like oblate spheroids.
yep.
Because of their rotation, they're squashed at the poles and larger at the equator.
And they're not really in equilibrium. They're all breathing in and out.
That's right. So it's highly more complicated. But you start with the simplest.
Right.
You build a model. Then you compare your model to observations. And if you find they're close, but it's not a perfect match, then you go back and alter your model
Right.
based on data.
Based on data and observation.
Yeah,
So,
and hopefully you get something but that doesn't even mean it's real, quote unquote, even if you match all the observations, because you have some ad hoc model that you tweaked. I'm thinking like the geocentric model of the early solar system.
yeah,
where
the
you
early
put-
one.
You put all these epicycles within the gears and stuff and all these mechanisms, and you get to a situation where empirically your model reproduces the observations being what you see with the unaided eye. And you
Right.
look up in the sky, the model predicts the location of Jupiter tonight at midnight. You look up, there's Jupiter, the model's got to be right? You wash your hands of the ordeal and move on to something more interesting.
Yeah, well, that's like my roommate. One time he was sitting at his computer and all of a sudden it stopped working. And the next thing he knows is smoke is just pouring out of the computer. And so we came up with the empirical idea that, the model that computers aren't chips of silicon that are working with electricity. They're little magic boxes of smoke. And if your smoke gets out of the computer, it stops working.
So what was your friend doing on the computer at the time? Do you know?
I have no idea. I know he was typing away, so I'm figuring he was putting together some paper or other.
So in other words, computers, if you do homework, they tend to go to be smoking. They go to smoke.
That's the other thing. They start losing smoke when you're doing homework. Yeah.
They pick up smoking, the bad habit.
So that's another addition onto the complication, onto the model we had.
And so in science, when we have models, even though they may explain all the observations we have at that point, if they're not based on some physical facts or understanding, they're just made up, they're not going to be correct. That's not the way science works.
Right.
And of course, your models also would make predictions.
I was about to say, we may still use that model because
Yeah.
it makes good predictions, but where we want to be is where we can say, this is why the model works.
Yeah, that's where you want to be, based on
Right.
a logical train of deductions and reasoning based on the known facts.
Yep.
And so you're always striving to, being able to make predictions and then test those predictions. Or if something new comes along, that somebody makes an observation or does an experiment that we didn't even think about before, then you can check it with your model and see
Right.
if you can explain
See if
those
the
new-
model
the
can
new
explain
data,
things,
the new
the new
observation.
data.
Yeah.
If it can't, you trash the model.
Yeah. And
Or,
that's,
well, you may trash the model. The question is not whether the model is incorrect. It's whether and how incorrect does it have to be before you stop using it.
and a classic example of that is Galileo.
Right.
So Galileo, through his telescope, saw that Venus went through a series of phases, and not only that, anytime when Venus is nearly a full phase, it was the smallest in apparent size through the telescope. Anytime it was a crescent phase, it was the largest in apparent size. So if you use the models of the solar system at the time, you had the Earth-centered model and the Sun-centered model. Only the Sun-centered model can explain those observations. So
Right.
they were totally new observations that never existed in the history of humanity before Galileo.
Right.
So no one can tweak their model to try to compensate for these observations because they didn't know they existed. And so you take something totally unexpected and check your models and you find one model seems to be the correct one. The other one isn't. So there goes that other model.
Right.
So that was the end of the Earth-centered model. But it's not like the Sun-centered model was perfect at the time,
Oh, absolutely not.
because one of the predictions from that model is the Earth is orbiting the Sun, therefore the stars should shift back and forth, that stellar parallax.
Right.
And they didn't see it because they didn't realize the stars were just so far away. The parallax is so tiny you can't see with your eye. You need a good quality telescope to see that parallax.
Right.
In fact, that wasn't observed until the 1800s by Bessel,
Right.
the Bessel function
The
guy.
Bessel function guy.
And he observed the first stellar parallax. And of course, nowadays we've seen millions and even billions of stellar parallax.
Yep.
So it proves that the Earth does move.
Mm-hmm. I agree. Yep.
So these
getting back to black hole jets.
So so the interesting thing about these jets is that they're extremely long in length. For example, they were picked up by the radio array, LOFAR. So this stands for low frequency array. It consists mainly, it's a core that's located in the Netherlands, but they're spread out among several countries, the antennas. Altogether, the array consists of about 20,000 antennas.
Oh, wow.
Yeah, it's amazing.
Holy cow.
And they're not that large. They're actually quite small. In fact, I should have had a picture of what one of them looked like. In fact, we may have a guest on in the future, Robert, to talk about LOFAR.
Okay.
And some of the results
Sounds like fun.
coming from it.
I love interferometers.
Now, this particular array is sensitive to long wavelengths. That's where you get the low frequency part of the name. And you were talking about wavelengths on the order of roughly 1.3 to about 30 meters.
Okay.
So very long
That's
wavelength.
really long wavelength.
Yeah, and it's really a relatively unexplored area of the electromagnetic spectrum for astronomical observations.
Well, I mean, that long wavelength, any kind of thermal activity is going to cause you noise. So, yeah.
So using this array then, at least for some of the data here, it was discovered the jets. And the jets you can see illustrated in the main image here. There's a line that stretches from the upper left to the bottom right. And on that line, there's a length scale, 7 megaparsecs.
Holy cow.
So these are huge. Now, to give you an idea what that means. So number one, a parsec is 3.26 light years.
Right.
So a megaparsec is 1 million parsecs. In other words, 3.26 million light years. So 7 megaparsecs is on the order of about 23 million light years. Now think of the size of the Milky Way.
The Milky Way is only 100,000 light years across.
That's the nominal size, the diameter that we use. If you include the dark matter halo, so you can extend the size of the Milky Way. You know, you can do out. Some people suggest 150,000 light years across, right? And so you'd have on the order of about 230 times the diameter of the Milky Way going from one end to the other to cover a distance of about 7 megaparsecs. 230 Milky Ways.
So these are mega scale.
These are mega scales. These are huge.
Intergalactic
as far as I know,
scale.
this is the largest jets ever discovered in terms of their length scale.
And I'm looking at them there, and I'm seeing bright spots at the ends of one side of it, and I'm like, what is it slamming into?
Well, if you can look a little closer, and the next slide will show you. So that sort of brings out the center area a little better. You can see the different sources of the jet itself. So jets are not uniform; they have these knots, and then we see that. Right. It's nothing unusual. But where they're so long, they will do, if you like, they will affect their environment. Right. And I don't mean the local environment.
Yeah. Right? Well, 7 megaparsecs long.
Yeah, that's right. So you think of a galaxy that's an active galactic nuclei, which means it has a supermassive black hole at its heart and the accretion disk. And if it has jets, these jets then can interact with the environment around the central region of the galaxy. But here we're talking about huge scales, 230 times the diameter of the Milky Way. These jets go way, way out. So not only do they affect the host galaxy, they're going to affect nearby galaxies and structures.
And that gets to my question. What are they slamming into that they brighten up?
Well, they're slamming into other material in the large-scale structure of the universe. Right. This particular black hole is 7.5 billion light years away. 7.5 billion light years.
Wow.
So it has been going. Now, how long has the jets been going, right? You can put estimates of it. But as far as we can tell, they've been, there a long time. Right. So we would have a long time to do damage, if you like, to the nearby environment. In fact, if you look at how galaxies are distributed over very large scales, we call that the cosmic web, the distribution of matter.
Because if you look up a picture of it, it looks like a spider web. Yeah. A very ugly spider web.
Looks like a three-dimensional spider web.
Yep.
Now, like a spider web, there are areas where there's voids, and then there are areas where there is the spider thread, the filament, if you want to call it, on the outskirts of the voids. So some of these voids that we have in the large-scale distribution of galaxies are, millions of light years in diameter. Now, how do you create those voids? People have often wondered, is it a natural byproduct of just the simple way that matter is distributed early on in the history of the universe, and then gravity just does its thing? And of course, along with that, you have to add in extra ingredients like dark energy.
Right.
Do you naturally get these voids? And people do complex supercomputer simulations that take months and months and months and months to complete, and you can reproduce that type of structure. But there's always been a question of, is there anything that can help these voids? Well, here's a way of helping. These jets can clear out that material over a huge volume of space and actually give it a jump start to the formation of these voids.
Okay.
Whether that happens for every void or this is such a rare phenomena, we don't know. And people are actively looking for these type of systems beyond this one system to see if there are a lot more out there, and how many, how abundant are they?
The way to think about this is these jets are like a wind, and it's blowing into a fog, and it'll blow a cavity out of that fog. That's essentially what's going on.
Yeah. So it'd be interesting to know what kind of impact these type of structures have. And not only that, what does that mean for the evolution of galaxies to begin with, the early stage of galaxy formation?
A jet with that much energy, if it slammed into a galaxy, it'd strip the galaxy. Wow.
And eventually, and you need the raw material to create these jets. And the jets need to be going for a long time, because how do you reach length scales of 23 million light years?
Right.
7 megaparsecs. So that's a time scale argument of how long these jets have been running to get that far. Right? They're not going to be traveling at the speed of light. It's going to be slower than that, because you're talking about the release of charged particles and so on. And so you're going to there's a lot of time, millions of years for these jets to be produced. And how long do they maintain themselves?
How much mass is involved in it that you can see it from that far away? I can see why you brought these up, because that's some exciting things to think about.
And remember, LOFAR is the instrument that captured these things. So this is a new, if you like, semi-new region that we're searching for at these very low frequencies. So what else is out there that we haven't noticed before? Because they're extremely hard to detect, and the other parts of the wavelengths of light that we looked at, right? So, and then also rare things, right?
Right.
So it's only when you survey a very large volume of space, you start to pick up these golden nuggets.
And this is why you want to look at all kinds of different wavelengths. You don't want to look just at visible wavelengths or infrared. You want to look at gamma rays and X-rays and microwave and now radio.
And it really captures your attention.
Yeah. So, speaking of capturing,
also been published in September, so recent, is once again a study looking at the possible origin of our moon, and to be fair, of other moons in our solar system, and by extension to other solar systems as well.
Right.
Because nowadays, if you do any work or research on the early formation of structure in our solar system, you're also doing it in terms of solar systems that are going around other host stars.
Other planets, yeah.
And we know of thousands and thousands of planets that are going around other stars. So there are many, quote, solar systems that we need to look at. And they're not all going to be the same, clearly, right? There's going to be a dispersion of properties.
Well, I don't think we have any Jupiter-sized planets going around our star that, have orbital periods of days.
No, so they'd be quite different. That's right.
Quite different.
And a lot of that, of course, so what Robert is referring to, in case you don't know, is that a lot of the solar systems that we've detected, so planets going around other stars other than our sun, those have shown that there are massive planets close to the host star, so they go around in a very short period of time, way closer than the planet Mercury is to our sun.
Right. For perspective, Mercury goes around the sun in 88 days, roughly.
Right.
We have planets the size of Jupiter going around their stars in 2 or 3 days. So they're really close to the star.
And then those type of systems then are easy observable given our present technology. So the observations are biased in a sense that it's much easier to pick up massive objects close to the host star. So those are the ones you're going to pick first.
Right. because they have the biggest impact on both the brightness of the star, the motion of the star.
Yeah, the radial
all that
velocity
sort of thing.
measurements, so the motion of the wobbling motion of the star
Yep.
due to it being tugged in various directions from bodies that orbit it.
Right.
And that's what we look for, the wobbling motion. In fact, that's why you can't hide the presence of planets in our going around our own sun.
It's because they affect the motion of the star.
Yeah, and anybody with the advanced technology, even if you're many light years away, you could look at our own sun and infer that there are planets going around our sun and even estimate order of magnitude estimate of the masses of some of the planets.
Right. So what's going on with this binary exchange capture theory?
Right. So you want to maybe say something about what is presently, not talking about this paper,
Okay.
but what is the leading explanation for the origin of the moon?
The leading explanation for the origin of the moon is that a body roughly the size of Mars impacted Earth at a very oblique angle high up towards one of its orbital poles, and that collision threw material into orbit around the now combined planet, and that became the moon.
So how long ago would this have happened?
This would have had to have happened very early on in the solar system, so we're talking 3.5, 4 billion years ago at least.
How, for something that happened, let's say 4 billion years ago,
Mm-hmm.
how would you even consider the evidence that would tell you if you're right or wrong in your hypothesis?
Okay. And that is one, how we know it's an oblique angle and all that is again through, as we were discussing earlier, computerized models. They put in a mathematical model for how things work, what the outcome is, and they look what can produce that outcome. Now, we have other things that point out whether or not these are reasonable outcomes, like we have material from the moon and we've checked its isotopic composition. It matches Earth, which means it couldn't have formed somewhere else in the solar system and moved in. It is basically, the moon is the same stuff as Earth.
So it could have formed nearby the Earth
It could have formed very nearby.
because the Earth itself had to form from something.
Right.
So it would be particles, material in the protoplanetary disk that represents our early solar system.
That's why we know that those matching isotope ratios mean they had to form very similar location in the disk, is because much as the planets differentiate with the much of the heavier material, like iron, being in the center of Earth, so too these disks differentiate with heavier stuff being closer into the center towards the sun, and lighter materials being out towards the edge. That's why Jupiter is hydrogen and helium, whereas the inner planets are iron, silicon, oxygen, and things like that.
So
Heavier elements.
The so-called terrestrial or rocky planets,
Right.
the Mercury, Venus, Earth, and Mars are
Right.
closest to the sun, where planets like Jupiter, Saturn, Uranus, and Neptune, the gas giants, they would have lots of volatiles that would be, evaporated off that material.
And that's kind of the key that leads to this differentiation, is these materials are evaporated. They're blown away by the energy of the star, in this case, the sun.
And so if you wanted to get a primordial, at least as close as possible, as pristine of sample of early solar system material, you probably want to go in the outer solar system.
And that's why we're interested now in the outer solar system. Yes, because that's literally the icebox from the formation of the planet.
And that reminds me, Robert, today is October the 1st. What's going to happen on October the 10th? Do you remember? Related to what we're talking about.
October 10th.
October
There's
10th.
Something that's happening that I know.
I know, because I just told you something's happening. But what is... No, just kidding. So do you remember a past podcast that we talked about something occurring on October 10th related to gas giants of the solar system?
I know I should know. Oh, no. No, I can't think of what it is. I know it's something to do with something that was launched, but...
Europa Clipper.
Oh, it is being launched. Okay. I was thinking in terms, from the way you were saying it, something was sliding into orbit around Jupiter or something.
No.
But it's being launched.
Being launched on October 10th. That's the current estimated launch date.
Keep your toes crossed.
Yeah, for sure, because it'll be 2030 before it actually get to Jupiter to start its science operation. So we have to wait a while.
Let's see.
6 years.
I don't want to think about how old I'll be then.
So this new paper then, the new ideas, is that they're talking about actually two objects
Right.
rather than a single object like you mentioned that passed by the Earth, that impacted the Earth, ejected material out into space,
That
ultimately
material
coalesced to form the moon itself.
Yeah.
And there's even a name given to this hypothesized
think I remember
body.
it's
It looks the
Theia.
size of the and mass of Mars.
Right.
And what's the name of it?
I think it's Theia.
Yeah. So that's the current ideas that we have, right? That slammed into the Earth. And would that eject more of the mantle and the crust rather than down even deeper, right? In the core region.
And we know from measurements of its moment of inertia that the moon is not differentiated. So it has a core, but it's very tiny. So it's pretty much rock that we see on the surface throughout. So, yeah.
And that would be consistent with that idea, right? That
Right.
it came from the mantle, probably.
Came from the mantle material
Of the
instead
Earth.
of the Earth as a whole or a unique body.
Right. And so this idea is that you'd have two bodies that were in orbit around each other, a binary type of system. And that orbital interaction would cause then one of the bodies to go in orbit around the Earth.
Right.
So on this diagram, and this is all done through computer simulation. Of course, nobody was
around
to actually see. So you're trying to say what is the most likely scenario and how do we test it?
Right.
That's the ideal here. So these are computer simulations. And you have two objects. So if you look at the diagram, let's say on the far left, prograde, you have two bodies, M1 and M2, that are in orbit around their center of mass. And they're also interacting closely with the second body that's on the far left, M sub P, so the mass of the planet, let's say the Earth
Right.
in this case. And through this interaction, one of the bodies gets captured by the Earth, if we're going to use the Earth as an example here. Ultimately, that would be our moon, where the other body gets slung out of the system. It gains enough kinetic energy and it's gone.
Right.
So that's one idea.
And it would have adjusted the Earth's orbit at the same time. So
And you can also have just the motion being the opposite here. Notice that M1 and M2 are orbiting in a different direction. And that's the cartoon or the drawing on the right side under retrograde. So the simulation tested both examples. If you have the two going one way relative to the Earth, what happens if you have the M1 and M2 going in the other way relative to the Earth? And notice you got the Earth on the other side.
right.
So they're trying to test both prograde and retrograde type of interactions here.
And it'll make a difference because it changes the kinetic energy and the torque and everything.
Yeah, so the idea is you want to capture a body, but you don't want to have that body always coalescing with the Earth, because
Right.
that won't work. And you don't want to have the interaction being such that both particles, M1, M2, get ejected from
Get
the
ejected,
system all the
yeah.
time, or at least most of the simulation runs that you make.
Right.
And the thing about simulations is you got the beauty to redo that experiment, if you want to call it that, over and over and over and over again, and changing the parameters
Right.
from
Which
one
is
simulation to
what
another.
these graphs are showing.
Which is what these graphs
various-
are showing.
yeah. Various parameter spaces of the escaping body's mass, the captured body's mass, and let's see what else. Oh, the velocities they're coming in at, and things like that.
Yeah, trying to see if there's any reasonable parameter spaces, we would say, where you would have a moon-like object being captured by an Earth-like planet.
Because that's one of the problems with the capture theory. All capture theories that the moon was captured by Earth is the moon compared to Earth is very massive. And so it would tend to just keep on moving through the system instead of being captured by Earth. And what this is saying is that then there was another body that slowed that one down in its movement that the Earth was able to pull it in. So,
And you think about that, you kind of, it gets back into trying to understand if there was a large body that collided with the Earth, let's say 4 billion years ago, where is the core of that body?
right. And the answer to that is of course that it would have differentiated out and slid down and merged with the core of Earth. That happens on some fairly short time scales. We've done experiments where we've looked at the viscosities and diffusion rates of materials at very high pressure. We can get with diamond anvil cells to the core mantle boundary pressures. So where the core and the mantle are meeting, we can reach those pressures with a diamond anvil cell. And doing that and looking at diffusion rates, how fast things move through each other and things like that, we can tell you that an iron core from this planet would have merged with Earth's core And it wouldn't have been on geological timescales. In other words, it wouldn't have been hundreds of millions or billions of years. It would have happened on the order of a few 100,000. So, yeah,
So how
very quick.
So I know, Robert, you've studied this. In fact, the talk that you're going to give on October 14th
It's going to be related to this. Yeah.
related to planetary interiors. So you want to address the issue of how the heck do you know what's going on deep inside the Earth itself? What are the instruments or tools that we can use?
Okay, and the answer to that is primarily it's seismic data. We can look at the various waves that earthquakes produce, and from their reflection, their refraction, their polarization, and things like that, we can tell what's going on, what happened to these waves to make those properties, and say, okay, this is going on, this is the structure. As far as the chemical composition of the mantle in the deep earth, well, the mantle we know because there are a few places where the mantle is actually exposed. The mantle is not molten like most of us tend to believe. Well, how can it not be molten at those temperatures? Well, if you squeeze ice, does it turn to liquid? No, it continues to freeze harder and harder and harder. So when you put things under pressure, they go from molten back to solid. Well, they would normally be liquid at surface temperatures. So we have places where the mantle is exposed. We have places where, like the Hawaiian volcanoes, which are sourced in the mantle, and they dredge up mantle material. So we know what the chemistry and properties of the minerals that make up the mantle look like, and they look nothing like the crust. So then we go to the lab and we mix up that chemistry, put it under pressure in various types of presses, and heat it up. And so we then can observe this is the type of mineral that comes out. This is the type of crystal. This is the wave speed of these things, of sound through that, which is then seismic waves. They're just sound waves. So we've got all kinds of methods that we can actually test what we think is going on, even if we can't drill down there.
Now, seismometers, how many of those cover the Earth? There must be literally tens of thousands.
Tens of thousands. I mean, there's a traveling array made up of hundreds that moves across North America. So,
So what's that about? I never heard of that.
I forget what its name is, but, it has just hundreds of geophones. They pick it up, lay it out in a particular pattern in a new location. Then they'll get data, pick it up, move it to a new location, lay it out again.
So I guess if you had the funding and the ability, you just have it stretch right across the country.
Right.
So you wouldn't have to move it at all.
And then outside of that array, because the shape of that array also improves what type of data changes what type of data you can pick up and infer from it.
So you get better resolution.
Better resolution. But we have randomly distributed geophones everywhere too. They got some at Mount St. Helens. They've got some monitoring other volcanoes. They've got some monitoring North Dakota, I'm pretty sure.
Yeah, I mean, you think of how would you ever tell if there were like multiple nuclei?
Yeah.
Because in the scenario of the moon capture, so here you run simulations with all different input parameters, trying to get something that seems to work.
Right.
And let's say it works 1 out of 100 times. You might, okay, so there's a 1% chance this may have happened for real.
Right.
But if you run it and it takes 10 million times to get one that works, then your odds of it actually happening is pretty low.
Pretty low.
Pretty insignificant.
Yeah.
And so this is one of the successful simulation runs that you see here on this slide, where you can actually get a body that gets captured ultimately by Earth-like planet, and that will form an Earth-like moon.
Okay.
But the probability is to get all of the orbital characteristics that you...
Well, let's see. What does it say?
That's the mass of the Earth. So you have the two incoming one on the bottom right, because that's they're orbiting around each other. So that's the wobbling back and forth that you see there. And the dashed line is the outbound object, which has 0.01 Earth masses. And the other object is 0.005 Earth masses.
Which is roughly the moon.
Yeah.
So, yeah, I'm just seeing if they list the probability. And they list plenty of other parameters,
It's in
like
the
the
paper.
period and everything else. But
they mention that the probability is low.
okay. And that's a really eccentric orbit. So that's really elliptical. How would you have circularized that?
Oh, tidal interactions, just like what occurs, with the moon.
Okay.
Why the same face of the moon points to the Earth.
Oh, so in
So very
tidal
early, yeah. So you have
locking, it would have
billions of
circularized it.
years
Okay.
for the
Okay.
orbit to
I'll buy that.
yeah. But whether it happened or not, I mean, who knows?
Well,
And the authors even admit that this is potentially one way
right,
to make the moon, but it doesn't mean that it happened.
right.
But it could have happened maybe in other situations, other solar systems, not just ours.
Because this model has to then also meet the criteria that the other observational criteria we have. The composition of Earth and Moon is is really similar. The shape of the moon bulging towards Earth and flat towards the back, which would suggest that it was molten at one point, and just various things like that. You've got to explain by this. So,
Question.
yeah.
If the moon was carved out of the mantle material and crust of the Earth early on, why doesn't it have the exact elemental composition?
Oh, now that's a good question, isn't it? And the answer would be because it might have been mixed in with the composition of Theia, the impactor. And that's the going explanation of why it's not identical, is because some of this other body's material, which would have had a composition different from Earth, got mixed into formation of the moon.
And based on how far apart they are, that is, their differences between the Earth and the moon, can't you put constraints on what was the mass, the amount of material that came from the other body?
Right, and we can even make guesses, good guesses with reasons behind them, but there's still speculation about where Theia, the impactor, would have formed in the solar system. So, yeah, you start being able to make these predictions, and then you just got to, as we've said several times in this podcast, once you make the predictions, you go out and make observations, make tests, run things in the experiments in the lab, and see how well what you predict comes out of what you can do.
But Theia must have been relatively close,
Right.
right, in terms of its compositional makeup to the Earth.
Yeah, it couldn't have been out where Mars is, for instance.
Right, so you can put really tight constraints on where it was in the early solar system.
Right, because the composition of the moon is not enough different that Theia would have necessarily been really different. Mars composition, we usually use the oxygen isotope ratio because there's more than one isotope of oxygen, more than one weight. And so, for instance, Mars's oxygen isotope ratio is much different from Earth's. It's significantly different. And that, again, has to do with that differentiation of the disk. The heavier elements, the heavier versions of oxygen stayed towards the center. The lighter ones got blown out.
You know, one of the things I found amazing in the late 1990s, so roughly in the mid-1990s, we started detecting planets going around other stars, that people proposed the ideal of planet migration, that planets actually newly forming planets can actually move in the early solar system through interactions of the material that's in that disk, early planetary disk.
And it's because, bottom line, it increases the drag.
Right. So,
on the planet.
And not only do you have incoming migration, but there is even ways of going outwards.
Right.
In fact, it was proposed, I think Norm Murray at the Canadian Institute of Theoretical Astrophysics, CETA, even proposed that you could look at the spectrum of stars, look at the metals, and actually put constraints on that a planet or planets could have went into that host star early on in the formation of those planets, contaminated the outer atmosphere with these metals, and that's what you're seeing in the spectrum of these stars.
Yeah. And the thing, I'm going to point this out. When we astronomers are talking about metals, we mean everything heavier than helium. Everything heavier than helium is a metal.
Right.
So we usually use iron, though, as the proxy. So, you know, the other thing to remember, so what we're looking at is the spectrum of these stars. We're seeing more iron, more carbon, more of these things than we'd expect. Well, where did that come from? Because it's clearly smeared out across the photosphere, the surface of the star, else we wouldn't be able to see it. And so the answer to that is it ate a planet. The planet got smeared out across the surface. Depending on the size of the star, that could last for a short time because it gets convected in and mixed into the star. Or it could last for a long time if there's no outer convection and you know.
I wonder if you could do a detailed study of a stellar nursery looking for stars that had abnormally high elemental abundance of iron and so on, to put time constraints on how long it's been since a planet, got swallowed by the star.
Yeah, and that could give you some constraints then on planet formation times, because
Definitely.
if it's a young star and it ate a Jupiter, which was what it would take for us to detect it in the spectrum of the star, probably. I don't know.
You can
Maybe
envision
not.
solar systems which were depleted of all their planets.
Right.
Because the vast majority of them, except for maybe some low ones out on the fringe, all migrated inwards like a train,
Right.
like a conveyor belt, ended up going into the host star, and then that's it.
Yeah.
Pac-Man at work.
And you see, this is also part of science. You ask questions and you then start thinking about, how could I test that? What would be the observable quantities that could come out of whether or not this happened?
In fact, getting back to the moon capture and the interaction of bodies within our solar system, we can put constraints on what type of interaction the Earth had early in its history with another massive type object, like a significant fraction of the Earth, could be 10%, just from the type of motion that the Earth has today. Because if it got walloped, let's say, by an object that's, 30% the mass of the Earth, and that happened 3.5 billion years ago, erosion, plate tectonics and all that would have got rid of the scar it left behind.
Right.
But its motion would still be there.
Right. Like a wobble to the axis.
Yeah.
Yeah.
And we talked about before where you could have multiple rotations around more than one axis, right? So that the Earth could have been in that situation.
Right.
And if it happened, we would know because it'd be like that today. But because it's not like that, we can put some interesting constraints on if objects have hit the Earth, and they have, put constraints on what are the most massive ones that collided with the Earth.
Right. And the fact that the Earth is here, we can put a constraint of nothing more massive than X could have hit it, because we wouldn't be here.
So we know that the Earth, after its formation, roughly where it is today, let's say after the creation of the moon as well, that there really hasn't been any significant sized body that impacted the Earth.
Right.
If there were some around in the early solar system, they went into the sun or got ejected outwards.
Yep. We have evidence for the largest impactor, recent impactor, and it wiped out the dinosaurs.
Yeah, but that would be like peanuts compared to what would actually do major damage to the motion of the Earth long term.
Right. No, I agree. Yeah.
You think of Uranus, right? Uranus is a weird planet.
It's flipped over on its side.
It's flipped over on its side. Now, how did it get like that?
Right.
Did a major body impact Uranus very early on in the formation of Uranus itself and cause it to flip?
Right.
What would do that? It's really, really bizarre. And I think that's the leading idea, if I'm not mistaken.
It is.
The problem is, how do you prove that? Or
How do you prove that?
What do you observe that would give you information to see if that idea is consistent or not with reality?
I can think of one observable, but we'd need a significant mass around Uranus to test it. And that is get moment of inertia and see if its central core, the solid core of it, was larger than expected for a planet that size and mass.
So what would you need to do that experiment?
Well, you would need something big enough, massive enough, that it significantly tugged on Uranus so that you could change its spin. In other words, change its torque to accurately measure its moment of inertia.
I'm just wondering, you think of an egg, right? You take two eggs, one that's been hard-boiled and one that hasn't.
Right.
And you can rotate them and tell which one is hard-boiled.
Right.
Just by their motion.
But you'd need to be able to tweak that motion of Uranus.
Well, I'm thinking about in the future, and there's been already a talk of proposals of a Uranus orbiter.
Right. And the orbiter may be able to do it.
That's what I'm thinking. Can we actually detect that a higher order rotational motion, a wobbling motion, if you like?
It'd be interesting to see.
By just having an orbiter going around and very high precision measurements of the motion of Uranus.
Yeah. I mean, it's possible.
That would be interesting.
It would be interesting.
I mean, today you'd have to use the moons of Uranus, but
right. So
that'd probably be much harder, right? Because they're so far away and it's hard to kind of map out. But having a probe directly in orbit around the planet,
that would definitely be useful for many more questions as well.
Yeah, for sure. So that'd be really neat when you think about it. But all of it, of course, is what? Science.
Science.
See? So if you want to do science, what's one way you could do it, Robert?
Well, you can come join us at the University of North Dakota, either online or on campus. And we have a lot of online degree programs that you can take advantage of wherever you are in the world. Or you can come here, come by and see Wayne and I, and, all that kind of good stuff.
Well, anyways, we're going to end this podcast for today. Our next one will be on Tuesday, October the 8th.
Mm-hmm.
We always leave you with a quote. So today's quote, fittingly, is from Galileo about the observation of Jupiter's moons.
Right.
We're talking about the solar system, so it all fits
Or the
in
Medicean stars, as he would have called them.
So here we go. You ready?
Ready.
Quote, "Here we have a fine and elegant argument for quieting the doubts of those who, while accepting with tranquil mind the revolution of planets about the sun in the Copernican system, are mightily disturbed to have the moon alone revolve about the earth and accompany it in an annual rotation about the sun. Some have believed that this structure of the universe should be rejected as impossible. But now we have not just one planet rotating about another, while both run through a great orbit around the sun. Our own eyes show us 4 stars, which wander around Jupiter, as does the moon around the earth, while all together trace out a grand revolution about the sun in the space of 12 years.
Nice. That was a lot to say. We've got the moon going around Earth, but it disturbs people that we've got similar stars going around Jupiter.
That's right. Pretty cool when you think about it.
Excellent. All right.
Thank you very much for listening.
Thanks, folks. See you next week.